Now, EIGRP was also designed to achieve sub-second convergence, but proper network design is an absolute must. So there are certain things that we can do to make sure that we can converge quickly with EIGRP. First is we can use address summarization to limit the scope of the queries. So we don't have to actually send a query until we lose the summary route. If we have more specific addresses there in our routing table, every time we lose a specific network, then we have to query for it unless we have a feasible successor. So that's actually another method to our network design, is to make sure that we have at least one feasible successor. See, by giving us a feasible successor, we can achieve that sub-second convergence because we don't have to go looking or querying for another path to a destination that we've lost. Another method in our proper network design is that we use equal cost paths where possible. So equal cost paths is something that EIGRP will figure out on its own. It'll figure out the cost of a path, and then it'll go ahead and load balance across equal cost paths by default. Now recall that with EIGRP we can configure the variance command, which allows us to do unequal cost load balancing. But again, in proper network design, we want to use equal cost paths whenever that's possible. Now, how important is having a feasible successor? Well, when it comes to EIGRP's convergence, it makes a big difference. It really does, because again, we don't have to try to query to get a next best path. So we want to have an alternate or a feasible successor in our topology table there, ready and waiting. Now, other methods that some will use is tuning the metrics so that they can achieve that equal cost load balancing, customizing metrics on a per interface basis. Remember, EIGRP uses a composite metric of bandwidth and delay by default, also uses reliability and load. But when we tune the metrics, it really has less of an impact than it would if we just simply use address summarization, limit the scope of our queries, equal cost paths, and making sure that we have a feasible successor. So when we have a really big network, it's not really practical to go in and tune the metrics on each interface. It really just doesn't make a whole lot of sense. Now, another thing that we want to do is we want to take our leaf nodes, so these would possibly be networks that are sitting out at a branch, or routers that are sitting out at a branch that are a leaf, and we want to configure those as a stub. Now, the reason that we configure those as a stub is because if I have a non-stub routing peer, then I'm going to query them whenever I lose a route. Now, if they're a stub, then more than likely they're not going to have another path to a route that I've lost. So by configuring them as a stub, it scopes our queries again. It limits the amount of queries that I need to send out and the amount of time that I need to wait to get a response back. So again, very important.